Okay, I'm recording, guys, but this is for Colin only, so only Colin will see the video, okay? Won't be posted on YouTube or anything like that. Right, so just waiting for others to get back. We're going to start out our next unit, which we are going to get halfway through, and that will encompass your midterm. We're going to talk about just energy before the midterm, and then after the midterm, we're going to talk about work. And then we'll take a test, we'll learn about momentum, take a test, and then relate linear momentum to rotational momentum. Okay, so momentum is going to help us move into our next unit. So I just switched the order of momentum and energy. So technically, we are doing chapter 8 first, then 7 in your textbook. According to the AP curriculum, work and energy is first in their curriculum. We're going to do work and energy first. So we're going to focus just on energy. We'll talk about 3 specific types, and then as we move through the year, we'll have some idea of how energy works, and we'll continue to build on those types as we learn rotation. Okay, so we're going to start with some general definitions, and then today we're going to spend most of the time going through problems. Okay, as we get to work, which is a little bit less familiar to us, we're going to spend a little bit more time talking about the concept. Okay, but energy we should be somewhat familiar with. Okay, and I see that Riley's back, so we're going to get started. So this unit is technically called work and energy, but again, we're going to focus just on energy for right now, before our midterm exam. Okay, so work is the transfer of energy. Okay, specifically mechanical energy, which in general physics is the only type of energy that we look into and account for. Okay, we measure energy in joules. Joules, Joules. We use a capital J to represent that unit, named it after a chemist for his work with chemical energy. Does anyone know what mechanical energy means? So work is a transfer of mechanical energy. So you think about a machine, right? Mechanical. What's occurring inside of that machine, what we can't see?
It's like moving parts, I guess.
Okay, moving parts, right? So mechanical energy is the energy due to the motion of an object or the object's position. Okay, so that is what mechanical energy is. So it's energy due to position or motion of a body or object. So energy due to position or motion of a body or object. Meaning that we're not taking a look at any energy transfer due to friction. Right, so when we use the words mechanical energy, we are basically pretending that friction doesn't exist, or friction isn't significant enough to be counted as a form of energy. So basically, we're ignoring friction when we use the words or the phrasing mechanical energy. Hi, Bree.
Hey, sorry, my computer died. I didn't know this.
If you're writing notes in classroom, we're focused on just the first 2 pages of those guided notes. This PowerPoint's also in classroom if you need to catch up. Okay. The energy we define, the general definition of energy is the ability to do work. Okay, the units we use for energy are joules, just as work. We'll talk about this a little bit more as we move through some examples, but energy and work are not vectors. They are technically scalar quantities, so they don't have direction. The types of energy that we're going to talk about today, we're specifically going to focus on two types. The first type is gravitational potential energy, which is a type of mechanical energy. And gravitational potential energy is basically the energy due to the object's position in a gravitational field. So its position from Earth's surface. Okay, so gravitational potential energy object possesses due to its position in a gravitational field. To calculate gravitational potential energy, we take the object's mass times our gravitational constant times height. So this is our equation here. You'll see it written two different ways. So U stands for potential. Okay, so U sub G would be gravitational potential. If you see U sub S, it's spring potential. So you'll see U representing any type of potential energy. You will unfortunately also see it written as PE equals M times G times H. So you should be able to recognize both. This is more correct, meaning at the university level, you'll see it written as U sub G. But as you're first learning it, so in high school physics, you usually use PE. Because if you watch, I know some of you said you watch Khan Academy videos, they'll probably have PE on Khan Academy videos. Versus if you watch a university lecture, you're going to see U sub G. But they really mean the same thing, potential energy. And the equation will tell you what type it is when you use PE versus the subscript. So it's the object's mass times gravity times the height above the surface or the zero line. The second type of energy we'll talk about today, I think there's a third type we'll talk about next week, is kinetic energy, which is another type of mechanical energy. It's the energy that an object has or possesses due to motion. So anytime an object's moving, it has kinetic energy. Kinetic energy is reliant on the object's mass and its velocity squared. You'll see that equation written as Ke equals 1/2 mv squared, or E sub k equals 1/2 mv squared. Okay, so today we're focusing on energy. Okay, we'll get to work a little bit later in the unit after midterms. Both measured in joules. Anyone need a minute to copy? Okay, so we say that mechanical energy, or the energy in general, is conserved. Specifically, when we're ignoring friction, we say that mechanical energy is conserved. So conservation of energy, which we probably know this, or have heard it before, hopefully, maybe in chemistry. Energy can never be created or destroyed, right? It just changes types. It transfers from type to type. The law of conservation of energy states that energy cannot be created or destroyed. It only changes from one form to another. Changes from one form to another. So even when friction is at play, energy is converted to thermal energy, but technically, the total amount of energy that was present before is the same amount of energy that's present after. When talking about energy on the AP exam, they like to pretend that all the surfaces are frictionless for the most part. Okay, so we can use this equation here. So capital ME subscript I is equal to ME subscript F. Okay, I'll explain this diagram in a second. You don't need to worry about it. Don't write it down. The next diagram is on your notes. Okay, and that's the one I will use to kind of explain this a little bit more. So, in words, what this means is that the initial mechanical energy is equal to the final kinetic energy, the final mechanical energy in the system. So that allows us to find missing information about that system if we know that energy must be conserved. And specifically, as we stated before, let's try to put attention to that, right? Mechanical energy is an energy due to an object's position or its motion. So our equation, if we were to expand it to its most complicated form, we have U sub G initial, so our gravitational potential energy initial, plus our kinetic energy initial would be equal to our gravitational potential energy final plus our kinetic energy final. And then we would have to plug in more specifically for what those terms mean. So I'm under the assumption that we have heard of kinetic and potential energy before. If that is not true, now is the time to tell me that. It is okay if that is not true, but now will be the time to tell me that. Okay, excellent. So as you can see here, right, when we shoot an object out of a cannon, we're starting with chemical energy. That chemical energy is converted to kinetic and potential energy as the object leaves the ground, right? It's moving and it's above the ground. It has both kinetic and potential energy. As it moves to the top of the path, right, the velocity in the y is 0, the velocity in the x is constant, so you have less kinetic energy, but more potential energy, the higher the object is from the ground. As we move back towards the ground, what's happening there? Steven? Okay, so as we move back towards the ground, the kinetic energy is going to increase as the potential energy decreases until we actually hit the ground, where we'll have kinetic energy. The amount of chemical energy initially will be equal to the amount of kinetic energy final, plus whatever energy was lost due to heat. Because of air resistance. Okay? But initially and finally, the amount of energy in the system will be the same. The type of energy has just changed. Numerically, it will be the same. Okay, so we're going to try a couple of AP examples. We'll do mathematical and conceptual examples. Okay, and most of them are, you'll see the pattern emerge as we move through them. I apologize, Lincoln, you've already seen this video last year. Discovered it during remote learning.
Okay, I like these videos.
So this guy here, his name is Mr. P. So he creates these videos called Flipping Physics. So I like teaching physics half time because I teach like 2 classes because he speaks up all of his time making these videos. But they're super, super interesting. He plays himself and then students, and it's great. So in this video, What I really like about it is that they are able to show the drop of the object, so how it's moving through the air, and the graph and data side by side instantaneously, which takes very impressive editing skills that Ms. McConnell does not have yet. So I'm going to use this video or this quick clip to show you how this works. So when we have a dumbbell, right, and we drop it from the top or its maximum position, it's initially at rest. Okay, so it's at rest, we have no kinetic energy. We have only potential energy due to its position above the ground. As the object falls, what do we expect to see? Kevin?
Kinetic energy will increase and potential energy will decrease.
Okay, so as potential energy decreases, our kinetic energy is going to increase. As it moves closer and closer to the ground, which we also call the zero line. Okay, the ground is the zero line. What that means is that the height at that position is 0. Okay, so let's take a look. At graphically what this would look like.
Potential energy of the object as a function of time.
Okay, so here's mechanical energy over time graph. This is the gravitational potential energy as a function of time. Right, so we start at a height, when we're at the highest above the ground, we have the most potential energy. When we hit the ground, we'll have the least amount of potential energy, right, as we expect.
Clearly, the gravitational potential energy of the object decreases as the height of the object decreases. We can add the kinetic energy to the graph as well, and you can see the kinetic energy increases as the height of the object decreases.
Okay, so right, the amount of energy is transferred from type to type. When we have no kinetic, we have all potential. When we have half of our energy as potential, half of it is kinetic. And if we were to graph the total mechanical energy, so the addition of potential plus kinetic at each time interval, we'll see we have a flat horizontal trend line.
But notice what happens when we include the total mechanical energy on the graph. When we add together at every point along the curve, the gravitational potential energies and kinetic energies, they always add up to the same value, 70.6 joules, or the total mechanical energy with which the object started. This is called conservation of mechanical energy. The idea that energy is neither created nor destroyed. Energy simply changes form. The gravitational potential energy is converted to kinetic energy as the object falls. That's pretty cool, Mr. E. The total mechanical energy stays the same the whole time the object is falling.
Actually, can you put the data table back up and add a column for the total mechanical energy?
Sure, I can do that.
Okay, so you'll see as height changes, right, we have all potential, no kinetic, and then the sum, however, of the two types of energies will remain constant throughout the entire path of motion. Okay, so this is a real life example. This data is taken using Logger Pro. Okay, so I'm not making this up, it's real. If, in this case, it's a drop from a relatively short height, air resistance will not impact the motion of the object significantly, so we can assume that mechanical energy is conserved. Okay, so let's take a look at how this would play out in a few AP-based problems.
4.
Okay, you can see here, this is on your page, when you add these together at each position, you'll get the same total amount of energy. Same total amount of energy. So initially, our mechanical energy will be 50,000 joules. Finally, our mechanical energy will be 50,000 joules. Okay. So in our first example, we have an object on an incline. Which are our favorite type of force problems, right? So in example 1, we have a block that slides down a frictionless ramp. This frictionless tells us that mechanical energy is conserved, and also that mu would be equal to 0. If the ramp is angled at 17 degrees, okay, so I'm going to just draw this ramp. For us. If you guys can't see, please let me know.
I could see it. It's all right.
I'm going to write bigger. Okay, so it's angled at 17 degrees. The length of the incline, so the length of our surface is 30 meters. The delta x is 30 meters. Find the speed of the block at the bottom of the ramp, assuming it started from rest. Okay, so the way that we're thinking about this, right? We want to look at initial and final. So initially, the block is on the top of the ramp and it has no velocity. So initially, the velocity of the object is 0. Finally, we need to figure out what the velocity is. So at the end of the motion, it's going to be here on the bottom of the ramp. We need to figure out what that final velocity is. We know mechanical energy will be conserved because the ramp is frictionless. So if velocity is 0, it starts with no kinetic energy. We know it has potential energy. So let's give this a shot. So I'm going to start out with my equation for conservation of mechanical energy. Initial mechanical energy is equal to the final mechanical energy. Our object can have initially potential energy, gravitational potential. It could have kinetic energy initially. That would be equal to the potential of the object at the end of its motion plus the kinetic energy at the end of its motion. So E sub k final. Okay. If initially the velocity is 0, will it have any kinetic energy?
No, it won't have any.
No. So 0, we can plug right in for that, for initial kinetic energy. How can we find the potential energy?
From the height?
Good. We need the height. So potential energy is the mass of the object times g times the height. We need to figure out what this height is. The height above the ground. H equals question mark. Okay, or you can call it delta y if you feel more comfortable doing that. If I have the hypotenuse and the angle, how do I find the opposite leg? Even. Sine. So when I take the sine of 17, that's going to be equal to opposite, which is h, over hypotenuse, which is 30 meters. And then take the sine of 17 and multiply by 30. And we get 8.7 7 meters. Okay? Let's keep going. So at the end of the ramp, we know it will have some final velocity. That's what we're interested in finding. When it's at the bottom of the ramp, will it have potential energy?
No, it won't have any.
No, at the bottom of the ramp, the height is 0. We call this the 0 line. Position where the height is 0. So there will be no final potential energy, only kinetic energy. You'll notice here that we're not given mass. When we simplify this equation, mgh equals 1/2 m times the final velocity squared. Why aren't we given mass? Kevin,
Because it's constant and it'll cancel out.
it's a constant, it'll cancel out, so we don't need it. If we divide both sides by m will cancel out. So GH equals 1/2 v final squared. And we'll plug in what we know. To save time, I'm just going to use 10 for G, like they do on the AP exam, even though that's not correct. Okay. So G is 10 meters per second squared. H will be 8.77 meters. That'll be equal to 1/2 times the final velocity squared. The biggest mistake is people forget to square the velocity. That's usually what goes wrong. So I get 87.7 meters. I'm going to multiply by 2 and then take the square root. And we get 13.2 meters per second squared. 13.2 meters per second, sorry, not meters per second squared. 13.2 meters per second. So notice here on this side of the equation, right, we have meters times meters, which would be meters squared, over seconds squared. And then we take the square root. So our units that we'll be left with are meters per second. Because mass cancels out, we won't have joules. 2 units we have are meters squared per second squared. So our units, our final units will be meters per second. Okay. Questions so far? Yes.
But that's like a problem. Is there any reason like why we should not just do it like with like kinematic equations?
Well, you would have to know and remember in order to do the kinematics equations. That's a good question. So if you're thinking kinematics, you know that the initial velocity is 0. You're trying to find the final velocity. You know that the length that it moves would technically be 30 meters. You need another variable, right? You need 3 variables to solve those equations. So let's say that you've memorized that the acceleration on a frictionless incline is g times the sine of theta. Then you can use kinematics. But if you don't have that memorized, you won't have enough variables, so you can't solve the problem. So that's why we have to use energy. That's why energy is useful to us. In situations where we don't have enough information or it'd be dangerous to get the information, we can use conservation of energy to solve. Good question. Other questions? All right, so let's take a look at a conceptual based question. This is a multiple choice question that's similar, or asks basically the same question in a different way. Okay, so this multiple choice question, we have 2 figures, ball 1 and ball 2. They both start from the same height, h1. They both end at the same height, H2. And this diagram is on your guided notes, right? What we're asked to find is which ball will be going the fastest at the end of the ramp. Okay, and we assume that they're both frictionless. So again, frictionless means that mechanical energy is conserved. So I want you guys to take a minute and think about this. We start at the same height and the end at the same height. How could we compare their final velocity? Steven?
I think that they're going to be the same
Okay, why?
because the mass is the same, gravity is the same, the initial or height 1 and height 2 are the same, and those are the only variables you have.
Right, so all of the variables, the heights before and after are the same. Even if the masses were technically different, right? Mass will cancel out when you're solving for the final velocity. So they should have the same speed when they're at the end of the ramp. And the way we can prove that is because, right, we plug in H1 for our initial height and H2 for our final height. When we solve for V final, our masses will cancel. I already canceled it out then. Yeah. So basically what we have is G times H1 minus G times H2 equal to 1/2 times V final squared. If I solve and rearrange for V final, right, I multiply both sides by 2 and take the square root. So my final velocity is going to be 2 times G times the change in the height, H1 minus H2. The square root of 2 times G times the change in the height, which for both balls, the change in the height will be the same. G is the same. That means the final velocity will be the same. So the answer here would be C. You'd obviously have a part D and E only. But the answer here would be C. They both have the same speed at the end of the ramp. So what this proves here is that energy is not path dependent. two objects can take two different paths and have the same amount of energy. If a quantity is not path dependent, that means that it's not a vector. So energy is a scalar quantity, right? It's not path dependent. Okay, let's take a look at another example where the object ends with both potential and kinetic energy. Any questions here before we keep going? Okay. Example 2, we have a roller coaster that is at rest at an elevation above the ground of 26 meters. It coasts down the slope and goes up a hill. All right, so I'm going to start by drawing the situation. So we start at an elevation. Okay, it goes down a slope. It's going to go back up a hill. The top of the hill is at an elevation of 16 meters, so about 10 meters lower than the initial height. What is the speed of the car at the top of the hill? Assume friction is negligible. So we're going to call this our zero line, where height is 0. When our roller coaster is initially at the top of the first hill, it's 26 meters above the ground. And it is at rest. So that means that the initial velocity is 0. At the top of the second hill, it has a height of 16 meters. Okay, we want the velocity V final when the car reaches that position. So we can use the conservation of mechanical energy. The initial mechanical energy should equal the final mechanical energy. Okay, so initial potential plus initial kinetic would equal final potential versus final kinetic energy. Initially, we have no velocity, so there will be no kinetic energy. We have only potential energy, which will be mgh. We'll call it h1. Finally, we'll have both potential, because we are a position above the ground, and kinetic, because the car is still moving. We're going to call 16 meters h2. I'm plugging in my equations for potential and kinetic energy. We see again that mass cancels. And now I'm going to plug in. I'm going to use 10 for g again just to simplify the problem just a little bit. So I have 10 meters per second squared times 26 meters will be equal to 10 meters per second squared times 16 meters plus 1/2 times the final velocity squared, which we are trying to find, so we leave as a variable. So I have 260 meters squared per second squared. I'm going to subtract over after I multiply. So I have 10 times 16, I get 160. And subtract that from 260 meters squared per second squared. That'll be equal to 1/2 times the final velocity squared. So I'm going to have 100 meters squared per second squared equals 1/2 final velocity squared. I'm going to multiply both sides by 2. I'll get 200 and take the square root. And write it up here. The square root of 200, I should get, I think it should be 14, right? It is 14, right?
Yeah.
Okay.
You can
Yeah, I had a square root of 1.
If you're exactly 14, it'd be 9.8.
I think it's like 14 point something. Let's see.
Yeah, get a little bit. I use 9.8 in my graph.
Yeah.
Exactly 14.
Even 14.
Yeah, it's 14.1 if you use 10. It's 14 if you use 10.8. Okay, so the final velocity of the cart at the top of the next hill will be 14 meters per second squared. Okay, so given this information, we couldn't use kinematics or forces to solve. So that's the benefit of energy, is that sometimes in some situations, it's easier to solve a problem given energy. Or it gives us another way to check our answer. All right, so let's break this up a little bit. Need my margin clip, right? Yes. All right, so we're gonna watch a quick clip of a movie that incorrectly displays the conservation of energy. So I'm gonna ask you while watching this to tell me why or how the physics in this video is incorrect. So what's wrong with this video clip? This is from like 2007. Does anyone see Norbit? At least we're all born at that point. There will be a time where no one will be born.
Okay.
Excuse the curse.
There's something wrong with the physics in that.
There's something wrong.
Oh no, it looks pretty realistic.
Yeah, you guys think that's what happens usually?
That's why they have the weight limit, so that doesn't happen.
Yeah, I think they do have a weight limit. But so what's wrong with this clip? There are a lot of things that we could kind of state. So don't. Go ahead, Steven.
Since mass cancels out, it shouldn't matter how heavy you are. You're still gonna finish at the same speed as someone else.
Okay, so if mechanical energy is conserved, meaning that there's little friction, then the mass shouldn't matter, and right, no matter what your mass is, you should stop at the end of the slide.
And when you're on wood, there's probably not a whole lot of
Should reduce spring protection.
Okay, so the water is meant to slow you down a little bit, but it will reduce the amount of friction. It's not as much friction as you between the slide. Okay, so technically, this person should come to a stop just like everybody else because mass shouldn't affect the motion. Okay, if mechanical energy is conserved. What else is wrong with this? So think about the second part. So besides the fact that she didn't come to a stop, after she kept moving, thinking about what we know about projectile motion, is what we saw just, is it what her motion after she went through the wall, was that possible?
Would have had to go up the line that down, right?
She would have had to start from a higher height
Yeah.
to land below in that fashion. Right, so she magically moves up into the air and then back down into the air without any additional force being
Right,
active.
you gotta watch the director's cut.
What was that?
That's in the director's cut.
In the director's cut. Yeah, so that shouldn't account. Okay, that shouldn't affect whether the object stops at the end of the ramp if mechanical energy is conserved. Also, right, we can't have projectile motion at an angle unless there's some type of force that's applied to it to get it moving in the x direction. It would be more like horizontal launch, but the slide would have to be above the kiddie pools for that to have occurred. Okay, so just another example of how Hollywood instills fake physics notions in our brains. Okay. This next example is going to relate projectile motion and energy. Okay, so this is a multiple choice question, concept question. So we have two stones, one of mass m and the other of mass 2m, which are directly thrown upward with the same speed. Okay, so I'm going to start there. So we have m and 2m, which are thrown directly upward. They have the same initial velocity. We don't know what it is, we know it's the same. We need to figure out which of these are true. Okay. So, the heavier stone will go higher than the lighter stone. So let's think about that. What kind of motion are we seeing here? An object thrown straight up in the air.
Curveball.
Parabolic path, okay. Or technically it's straight up and straight down. So type 3 free fall. So we have constant acceleration. Right, there's only acceleration in the y. There's only initial velocity in the y. So their accelerations will both be 9.8 meters per second squared. Their initial velocities are both the same. We need to compare their max heights. So their position here. Delta x and delta x. What else do we know about objects when they reach this position up here? Even?
Velocity 0.
Velocity in the y, right, is 0. So if we wanted to find delta x for either situation, and we have initial velocity in the y, final velocity in the y at that position, acceleration in the y, what big four equation could be used? So we have initial velocity in the y, acceleration in the y. We have v in the y, the final velocity at that point. We want to find delta y, I should say.
You can use v squared equals the initial velocity squared plus 2a delta y.
Okay, so v in the y squared equals v initial in the y squared plus 2 times a times delta y. Are any of these variables different? For either situation?
No,
Are you guys following me or no?
They would be the same in space.
Right, so if you were to plug in and solve for delta y, they would be the same. for both situations, regardless of the mass. If they have the same initial velocity, they have the same acceleration, they have the same final velocity, they're going to move the same displacement. Delta y will be the same. So that is not our answer. The acceleration is what affects delta y, not the mass acceleration. Yes, it would require two different forces to cause that acceleration, but if the acceleration is the same, they'll travel the same distance. Okay, in B, both stones reach the same height. Okay, so we know that part's true. Because they both have the same kinetic energy. So let's think about that. So kinetic energy initial, right? Is going to be 1/2 mv squared. Kinetic energy final will be 1/2 mv final squared. So at the top of the path, when they're at the same height, neither of them will have kinetic energy. So let's take a look at initial. Initially, will the objects have the same amount of kinetic energy?
No, they won't,
Why, Riley?
because one mass is larger than the other.
They have the same velocity, but their masses are different. So the 2m, right, will have 2 times the amount of initial kinetic energy. Right, 2m is larger than m. So this is not true. So the first part is true, but not because of the reason they're stating. The kinetic energy itself will not be the same. Kinetic energy by itself. Okay, C, at the highest point, both stones have the same gravitational potential energy. That is not true for the same reason again. 2m is larger than m. Potential energy is m times g times h. The potential energy itself will not be equivalent at the top of the path. So D, at the highest point, the heavier stone will have twice the gravitational potential energy, and that will be true. Okay, so M will have gravitational potential energy of mgh, while 2m will have gravitational potential energy of 2mgh. So the height is the same, g is the same, but the mass is not. So that leaves our only answer, which would be D. Okay. Questions so far? All right, so similar fashion, we're going to look at projectile motion in this next multiple choice question. I want you guys to give this one a try by yourself. Okay, if you want to talk to people or type in the chat if you're virtual, that's great. Because I'm going to have you guys work through this mentally, independently. So a girl throws a stone from a bridge. Which way should she throw this stone so that the speed of the stone will be the greatest when it hits the water below? The stone will be thrown with the same initial speed in each case. So initial velocity is the same. Our options, that did not show up at all. Our options are straight up, straight down, at a 45-degree angle, horizontally. The speed will be the same no matter how she throws it. So let's give this a shot. Okay, so tell somebody in your general area. So if you're with us virtually, type in the chat which letter you think. A, B, C, D, E.
I would say probably E.
That is what I said as well.
Yeah.
These are all gravity the same, like the same. Initial velocity the same. Final velocity. We got our answer.
Finally.
Put all my chips in.
First episode of WandaVision.
Really?
Yeah.
On Disney Plus, too.
Yeah.
I bet that was it. I didn't even realize. I assumed I didn't have it. And I was just like, on the side. It's like, oh, you get it. And then I like download the app, and it's just like, silence your extended.
Okay, so there's two ways to think about this. You can either think about projectile motion or energy. I think energy is an easier way to think about it, because there's really less variables at play with energy, right? You have M, G, H, and B. Versus with projectile motion, you have initial velocity, final velocity, the change in the height, the acceleration, time. So it's one less variable to think about. But whichever one you understand or like best is the way that you will probably approach this problem. So in terms of energy, you think about it in terms of energy. When we're first starting, what kind of mechanical energy do we have? Steven?
Yeah, you have kinetic and potential.
Okay, so you have kinetic and potential. You have mgh and 1/2 mv squared. We know the mass of the object is the same. The velocity of the object is the same. So the only thing over here that we need to look at or check back to would be the height, the initial height of the object. When it hits the water, what kind of energy will it have?
Kinetic.
Only kinetic. And that's what we're most interested in, right? So to help me picture it, I drew a diagram. Right, so it's thrown straight up, straight down, horizontally, or at an angle. What can we say about the initial height in which the object is released?
I thought it was the same. I assumed it meant like when it comes out of the girl's hand.
Yeah, so initially, when it's launched, it has the same height. Launched from the same height. It lands at the same height. No matter how it's thrown, it's going to have the same final velocity. Okay, so the simplest way to look at it would be in terms of energy, because we can see here that it's really thrown from the same height from the bridge, same distance above the ground. In terms of projectile motion, technically our change in our y is going to be the same, right? And the change in the y is what's going to affect the velocity in the y. So the change in the vertical height of the object will be the same, right? If it's thrown up, here's our change in height. If it's thrown down, here's our change in height. If it's thrown horizontally, this is still our change in height. It's the distance of the, or the height of the bridge. If it's thrown at an angle, our change in the height is still the height of the bridge. So if the vertical displacement is the same, acceleration is the same, it'll land with the same velocity. But energy is the easiest way to think about it. So our answer here is E. Are there any questions here? Anyone still not understand, like, why isn't D the answer? Because it's okay, we'll talk more about it. Okay. Okay, last one. Okay, so this is numerical example number 3. So we have an 8-meter rod is pinned to a frictionless pivot as shown in the figure. So this is on your guided notes here. The mass is 4 kilograms. It's attached to the rod. If the rod is released from the point shown in the diagram, what will the tension in the rod be when it passes through the velocity point? Okay. So really going to solve the first part of this question, the first half of it. So we have a 4 kilogram mass. The distance from the center of the circle to the mass itself is 8 meters. That rod makes a 30-degree angle with the horizontal. We're interested in the tension, or really what we want to find is the velocity at this point down here. So at the bottom of this path, this length here will still be 8 meters. We want to figure out the velocity of the object at that position. We're going to use conservation of energy to do that, right? So you want to find the final velocity of the object at this position. Initially, it starts at rest at this position here. So we know that the distance from here to here is 8 meters. We need to figure out how far it falls from here to here, right? We're looking at the height. This is our 0 point down here. The height is 0 here. From here to here is 8 meters. We need to figure out the height from here to here. So we actually did this once before in a similar problem. How do we find h?
Is it sine, I guess? Or is it,
Yes.
right? Yeah.
Right, so to find h, we're going to take the sine of 30. That's going to be equal to opposite, which will be h, over hypotenuse, which is 8 meters. We get 4. Sine of 30 times 8 meters, we get 4 meters. So this height here, this change in height, will be 4 meters. Let me write that down. If this is frictionless, a frictionless pivot, we know that mechanical energy is conserved. So mechanical energy initial will equal mechanical energy final. Initially, if it's released from rest, it will have only potential energy initially. There will be no kinetic energy initially. At the bottom of its path, its height we are going to assume is 0. That's our 0 line. So we'll have no final potential energy. It'll only have final kinetic energy. So our initial potential energy will be m times g times h. That's going to be equal to 1/2 mass times the final velocity squared. We are given the mass, but we technically don't need it for the energy segment of the problem. So now we just plug in. I'm going to use 10 meters per second squared times h. Technically, the initial height from 0 is going to be what? What's the initial height from the 0 line? What's the height from here to here?
12.
12. 8 plus 4. So the initial height compared to the 0 line will be 12 meters. 12 meters. So I have 10 meters per second squared times 12 meters, equal to 1/2 times the final velocity squared. So you get 120 times 2, I get 240. The square root of 240, I get 15.49, 15.5 meters per second. So at the end of the path, the object will have a velocity of 15.5 meters per second. If you want the total height from the 0 line. The path does not matter, right? Energy is not path dependent. It is a vector, it is a scalar, not a vector. So we want their total change in height, not the degrees in which it moves. Okay, for part 2, we have to come back to this a little bit later. Okay, for this tension is a centripetal force. Centripetal acceleration is v squared over r. We set t minus mg equal to v squared, m times v squared over r. Some of us have learned circular motion before, some of us haven't. So we're just going to stop here. And we'll finish that problem when we get to circular motion. Okay, so your homework for this weekend. I know that they have weird numbers just because the problems come from all over the place. I'm sorry. This is in classroom as well. So on that homework, you can do 4, 10, 104, 109, 110, 115, 129, and 9. And those are in the order that they're on the page. Yeah, so 4 is the first problem, 10 is the second problem. You're going to skip 6. You can do 104, 109, 110. So basically you can do the whole first page except for number 6. On the second page, you can do 115. So these two here, 115 and 129, and 9. So basically, you can do the first page, except for number 6, and stop after 9 on the second page. Should I give those a shot? This weekend. And they're multiple choice, so I will post the answers, but I want you to give them a try first. Some of them are conceptual, so I don't want to just give you the answer. So you guys can get started on that homework in a couple few minutes. Like 15 maybe. Stop.